Welcome to solverfy.
We're looking for an indicator for the titration of 0.25 molar C6H5COOH with 0.25 molar KOH, which also means just 0.25 molar of OH minus. And C6H5COOH has a Ka value of 6.3 times 10 to the negative fifth. In order to know what indicator we're going to use for this titration, we're going to want to know what the pH of this solution will be at the equivalence point. So first, 0.25 molar C6H5COOH and 0.25 molar OH minus will react to form 0.125 molar C6H5COO minus. This is because we'll have an equal amount of moles to the original C6H5COOH, but the volume will double since we're adding the same amount of C6H5COOH and OH minus. So now we just have a weak base problem here. C6H5COO minus will react with the water in the solution to form C6H5COOH and OH minus. And here we can look at an ice table. Initially, as we just saw, we start with 0.125 molar C6H5COO minus and 0 molar C6H5COOH and 0 molar OH minus. And liquids aren't used in these calculations, so we can ignore water here. Now for the change, some unknown amount, which we'll call x, will react to form an equal amount of the two products. Then at equilibrium, we just add initial and change. So for C6H5COO minus, we'll have 0.125 minus x, and for the two products, we'll have x. Now we know that Kb is equal to concentration of hydroxide times the concentration of the weak acid over the concentration of the weak base. We also know that Kb is equal to Kw over Ka. And we have all of these values in order to solve for Kb. So Kw, which is 10 to the negative 14th, over Ka, which we have here, 6.3 times 10 to the negative fifth, is equal to the concentration of OH minus, which is X, concentration of HA, or our weak acid, which is also X, so we can just have X squared up here, and then divided by the concentration of the weak base, which is 0.125 minus X. Simplifying this, we get 2.22 times 10 to the negative 10th equals X squared over 0.125 minus X. In order to make this calculation of solving for X simpler, we can make the assumption that this X is so small that it's not going to affect our significant figures at the end of the calculation, whether it's there or not. And we can make this assumption as long as we check it at the end and make sure that the assumption holds true. So then X squared equals 2.22 times 10 to the negative 10th, or X equals the square root of 2.22 times 10 to the negative 10th. This is equal to 1.5 times 10 to the negative fifth. Really quickly, checking our assumption, 0.125 minus 0.000015, which is X, is still going to be equal to 0.125. This means that our assumption holds true, so it is a valid assumption. And now that we've calculated our value for x, we know the concentration of OH minus, since that is what x is equal to. So our concentration of hydroxide is 1.5 times 10 to the negative fifth molar, and we can use this concentration to solve for our pH. pH is 14 minus POH, which is equal to 14 minus the negative log of the concentration of hydroxide. So our pH is 14 plus the log of 1.5 times 10 to the negative fifth. This is 9.2. So now we're looking for an indicator that changes color around a pH of 9.2, or more specifically an indicator that has a pKa value of approximately 9.2. This is true for phenolphthalein, which has a pH range of approximately 8 to 10, making it the perfect indicator for this titration up here. Now let's look at another titration. If we titrate ammonium, 0.5 molar ammonium with 0.5 molar OH minus, it will form water and ammonia, and the pKb of ammonia is 1.76 times 10 to the negative fifth. Similarly to the last problem, we have equal amounts of NH4 plus and OH minus, so that'll give us an equal amount of NH3, but double the volume. So we have 0.25 molar NH3. Then again, we have a weak base problem. So ammonia and water form ammonium and hydroxide. So I'm going to get the phases in here. Alright, now we can make a ice table. We start with 0.25 molar NH3. Again, we can ignore water since it's a liquid. We have initially 0 molar NH4 plus and 0 molar OH minus. Then for the change, we have an unknown amount of NH3 reacting to form that same amount of NH4 plus and OH minus. At equilibrium, again, we just add initial and change. And I just realized I made a mistake here. This should be Kb, not pKb. An easy mistake to make that will really mess up your calculations. Now, just like last time, we have Kb equal to concentration of OH minus times the concentration of our weak acid, which in our case is NH4 plus, over our concentration of weak base, which in our case is NH3. So Kb is then equal to x squared over 0.25 minus x. Again, we can try to make this assumption that this x here is negligible. So 1.76 times 10 to the negative fifth equals x squared, or x is the square root of 1.76 times 10 to the negative fifth, which is 4.2 times 10 to the negative third. Again, this means our assumption is valid since it will not affect our answer within two significant figures, whether we include this x or not. So now that we have our concentration of OH minus, we can calculate our pH. pH equals 14 minus pOH, which is 14 minus the negative log of our concentration of OH, which in our case is 4.2 times 10 to the negative third, and this is 11.62. So we're looking for a pH indicator that changes color at a pH of approximately 11.62. The indicator alizarin has two pKa values and therefore two pH ranges. The first one is about 5.6 to 7.2, and the second is about 11 to 12.4. Our second color change is a gray indicator for this titration here, since it includes the pH of 11.62 within its range.